Hello, my shimmering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW Gulf. Students, I welcome you all to your Triumph batch, and today we are going to start with ultimate recap session for the chapter Metallurgy. Yes, that is general principles and isolation of elements. Yes, students. So I guess you all are excited for this particular class. Why, ma'am? Because this chapter is a theoretical chapter, and many of the students face a difficulty in this one. Yes. So we are going to understand each and every concept with diagrams. Yes. So let's start the session with a beautiful smile. So as I've already said you that this is going to be ultimate recap session. That means we are going to revise the complete session. So it's a request to you, take out your notes. If you don't have made notes till now, you can make it. Yes, by it will be in the form like if you have an exam, if you'll revise it, it will be a quick form of notes revision. Yeah. Okay, students. So let's start our chapter metallurgy, students. Okay, how are we going to do? What is the today's target? So initially, students, we shall be starting with some basic terms. Okay, we will be understanding what is an ore, what is a metal, what is a gang particle, flux particle, types of flux particles. So all of the basic definitions, the basic terms will be clarified initially. Then we will be studying about the occurrence of metals, like which is the most abundant metal. Okay, on Earth's crust, we'll be understanding that. Then comes out to be concentration of force and the crushing process. Now we have various methods such as hydraulic washing, gravity separation, magnetic separation, froth flotation process, leaching process, the refining of the ores. Then is extraction of crude metal from the concentrated ore. This is cut, okay. Then basically is thermodynamic principles of the metallurgical process, a lingam diagram in which many of the students face a difficulty. Yeah, yes, the limitations, the extraction of the aluminium, zone refining method, vapor phase refining, all of these terms will be cleared over here. So let's start with the very basic terms. First of all, you should know that how does a metal occur. Metal can occur, students, in two forms. One is basically the combined form, another one is basically the elemental form. So here you can write it down. If I'll talk about metal, metal can exist in two forms, students. One is basically your combined form, and other is in the form of elemental form. Now, if I'll talk about the reactivity, students, the combined form is highly reactive. The combined form is highly reactive. Highly reactive. And if I'll talk about the elemental form, students, it is least reactive. It is least reactive. So you very well know what is a metal. Till now we have understood metal in our lower standards, the class 10th class and the ninth one. What exactly is a metal? Metal is basically the element which tends to form the positive ions. Yeah. Now our chapter starts from which term? What is a mineral? So mineral is that naturally occurring compound basically which contains metals. Yes. So now this is what is mineral. But what is an ore, ma'am? What is an ore? That means minerals we can naturally occurring compound. That means we can found it from the earth's crust. Yes. What is an ore? Ore is basically that mineral from which metal can be extracted. From which metal can be extracted. That means minerals from which extraction is possible economically. Yeah. So minerals from which metal can be extracted are referred to as your ores. Now this is an important definition. The next is gang or the matrix. Students, again an important part. See, when you are, separating out the, you are taking out the mineral from the earth's crust, there are so many unwanted particles, there are so many undesirable extra things that comes along with it, such as dust, sand and all of that stuff. So that basically is the gang particles, the impurities, in other words I would say, is the gang particles or the matrix. So what it is, undesirable impurities present in the ore is referred to as the gang particles. Yes. Then what is the mining process of taking out ore from the earth's crust is basically the mining process. Yeah. Here it will be earth's crust, right? Now, see, we basically know that we do have impurities, but when we are basically taking that, we are extracting a metal. If there are impurities, we need to remove it also. How are we going to remove it? We will be adding flux into it in order to remove it. So there is one more definition that you should know, that is about what is a flux. Substance added substance added to remove impurities. Substance added to remove impurities is basically flux. What is a flux? The substance that we add so that we can remove the impurities, or I would say the gang particles. Clear? Now what it is going to do, basically it is going to decrease the melting point of the ore. What it is going to do? It is going to decrease the melting point of ore. The melting point of ore. What else it is going to do? It is going to increase the concentration of the ore. To increase the concentration of ore. Now this was the role of flux. What is basically types of flux? Let us discuss that. See students, types of flux. See students, flux can be divided into three types first of all. One is basically your acidic flux. Acidic flux. Then comes out to be your basic flux. And last is your neutral flux. What is the role of acidic flux? Basically, acidic flux is used in order to remove the basic impurities. Used to remove basic impurities. Okay, basic flux is used to remove the acidic impurities. Used to remove acidic impurities. Yes. Now see students, let's take some few examples over here to understand in depth. See, if I say over here that I have SiO2 as my basic impurity. SiO2 as my basic impurity. I will add an acidic flux into it. So my acidic flux is FeO. This is my acidic flux that I am adding over here. Understand students, when you have to remove a basic impurity, you have to add an acidic flux. When you have to remove an acidic impurity, you have to add its opposite flux, right? So FeO, that is, it is acidic flux. Now one important key point that everyone should know about it, that is when you add flux and impurity, when you add flux into impurity, you are going to obtain slag. What are you going to obtain? Slag. So from here, when you are adding SiO2 and FeO, basically you will be obtaining FeSiO3, which is a slag. This is a slag obtained over here. In the similar way, if I'm talking about basic flux, here acidic impurity is present. So let's say again here SiO2 is acidic impurity. See, here it was acting as a basic impurity. Here it is acting as an acidic impurity. And as an acidic impurity, ma'am. So now in this acidic impurity, I'm going to add a basic flux. Yes. So over here, basic flux that I'm taking is CaO. This is my basic flux. So when I'm adding them together, what I'm going to obtain? Ma'am, we are going to obtain a slag. That is CaSiO3. So this is the slag obtained. This is the slag obtained from here. Everybody just write it down. Now again, the next part about neutral flux, if I talk about, neutral in this example is fluorospore, cryolite. These are the examples of neutral one. And the role is basically, it is also going to decrease the melting point of the ore. And it is going to increase the concentration of the ore. Okay. So basically neutral words itself says that basically which exhibits both the properties. Basically, if we'll talk about acidic one, it is going to remove the basic one. If we have basic one, it is going to remove the acidic one. In neutral example of fluorospore, cryolite, these are examples. Let's move on to the next one. Now students, comes your next part, that is occurrence of metals. Let us understand about this. If I'll talk about the most abundant metal, that is aluminium, which is found from the earth's crust. But if I'll talk about the abundance in terms of elements, aluminium comes at third number. In terms of metal, it is at first number. So among metals, aluminium is the most abundant. Okay, the first one. It is the third most abundant element in Earth's crust. If I'll talk about element, it comes under the third position. Yes. It is major component of many igneous minerals including mica and clays. Iron is the second most abundant metal in the Earth's crust. Okay, now students, let's talk about in which form do they exist. Basically, we have a metal and I have written their ores and actual what are the compounds. Basically, I will be letting you know that yes, students, you have to learn this because this are generally asked in exams. So you just have to put a tick over there in the NCERT that yes, you should know about this as well. So let's talk about aluminium. See, in aluminium, basically the more important ones are your bauxite, diaspore, and corundum. All of these three are important. All of these three are important. So basically, bauxite is basically Al2O3, then diaspore Al2O3 dot H2O, then corundum. So yes, you should know about it. Yeah, yes. Now, if I'm talking about iron, basically in iron, students, you have to, you should know about each and every one of them. Hematite, magnetite, siderite, iron pyrite. Iron pyrite is fool's gold. FeS2, right? And lemononite. So basically, iron ones, or you should know because they are very common and they are generally asked in an exam. So if you have heard about it, it will be easy for you as well. Let's talk about more now. See, there are some ores like of copper. If you'll see over here, these are for copper. And in copper, you should know for copper glans and for malachite. Both of them are really, really very important. If I'll talk about zinc, now for zinc also you should know about all of these three ores, that is zinc blende, that is ZNS, calamine, that is ZnCO3, then we have zincite, that is ZNO. And if I'll talk about lead, in lead only one is important, galena, PBS. It is asked in questions also about PBS. So this is again important one. You can put a star if you don't have, with NCERT with you, you can write it down. It is up to you, students. Let's move on to the next one. Now we have of magnesium. Of magnesium, students, very important is dolomite. Now dolomite is MgCO3 dot CaCO3. Okay, and yes, of tin, if you want to do, you can do that, but not that much important. That is calcitrite, right? Everybody just write down these are the metals and their ores, which is basically written over here for you people. Now let's talk about how we are going to start. What is basically how we are going to extract a metal. How is the metallurgical process going to take place? So the very first part is basically we are going to do the mining of ore. What we are going to do? We are going to take an ore. We are going to do its concentration. So initial step from which we are going to start is concentration of ore. What exactly is concentration of ore? Concentration in other terms is washing, clearing, cleaning. So this is what is concentration of ore. After concentration of ore, students, what exactly we are going to do? We are going to, do the conversion process. We are going to convert that ore into the oxide form. So concentration, that means cleaning. Now conversion into its oxide form. Yes. Now when I have converted it into its oxide, we are going to reduce it to metals. What it is? Reduction to metal, students. Next, ma'am, then is refining. And when we are going to do the refining, we are going to extract the pure metals. By this way, we are going to start, students. So let us proceed. The very first over here is concentration of ores and crushing of ores. See, when we are basically, cleaning it out, we have to crush it into the powdered form. Then only we can do the separation process. Otherwise, it is not at all possible. Here, when you are seeing the separation process, the powdered form of ore is taken. That means it is crushed, right? So basically, what is concentration? Concentration is cleaning. Okay, cleaning of an ore, washing of an ore. Now it occurs in two steps. One is physical separation, another one is chemical separation. Physical separation holds further three steps, further three methods. One is gravity separation method, another one is magnetic separation, another one is froth flotation. All of these three are very easy and very important. In chemical separation, we do have many more. Let's see. So first is hydraulic washing. Let's talk about what hydraulic washing, ma'am. So in hydraulic washing or gravity separation method, what we are going to do, you know that we have an ore, we have an impurity. You know this thing well. Now ore here will be heavier and impurity is basically lighter. Let me tell you in short, then we'll read it. Ore basically is your heavier. Ore basically is your heavier and impurity is lighter. impurity is lighter. Ore is heavy, impurity is lighter. So what will happen? Which will settle down? Which is heavier? Ore will settle down. Now, how it will settle down, ma'am? What is basically the technique? You will pass a stream of running water. What you are going to do? You will pass a stream of running water. What you're going to do, for example, if we have somewhat like this, okay, you will pass a stream of running water. So the ore that is heavy will settle over here, and the impurities will move down because they are lighter. Ore will settle because it is heavy in nature. Now, what it is, you are passing water, a stream of water over here. This is the process of hydraulic washing or the gravity separation method. Let's read about it in detail. It is also referred to as levitation method, if I'll tell you. Now see, the crushed ore is washed in a stream of water. Now the crushed ore, that means the powdered form of ore. The lighter impurities are swept away while the heavier ore particles settle down. Very important thing. Next thing. Iron ores, tin ores are concentrated by this manner. You should know about it. Okay. It is also known as gravity separation or hydraulic washing or levitation method. This is the very first method, everybody. Just write it down, students, because it is the initial method asked again and again in exam. So if you know about it, it's very easy one. It's a very, very easy one. Done this, students? Yes. Okay. Let's move on to the next one. Now the next one is magnetic separation. Here we are going to see when there is a difference in magnetic properties. One of them is non-magnetic in nature, another one is magnetic in nature. So initially when the roller is going to start, the non-magnetic will separate first and then the magnetic one. Let's see. The process is meant for the separation of ores from impurities based upon their difference in their magnetic properties. So the one which has a non-magnetic behavior will get separated first and then the non-magnetic. How? See. Here we are taking an powdered form of ore. This is powdered form of ore that we are putting over here. Now this is a belt through which the roller is going to rotate. It is going to rotate like this, okay? So when we are putting impurities over here, what is seen that here are two beakers kept. And here see what happens. The one which is non-magnetic in nature, non-magnetic one will separate over here and magnetic one will come over here. Magnetic one will come close to the roller and will separate over here, and the non-magnetic will get separated out. So by this way we can separate ore and impurities in a very simpler manner, in a very easy manner. This is what is about the magnetic separation method. Clear, everyone? Let's read more about it. Let's read about it. In this method, the powdered form of ore is placed over a leather bed which moves over the two rollers, one of which is magnetic in nature. When the crushed ore is passed over the magnetic roller, magnetic ore particles are attracted by it, right? And it will fall nearer to the beaker, nearer to the roller because it is magnetic. And the impurities basically falls away from the magnetic roller because they are non-magnetic. Now, chromite from siliceous gangue, rutile, that is TiO2 from chlorapatite, and wolframite from cassiterite are separated by this method. How magnetic one are separated from the non-magnetic one. How ore is separated from the impurity. Let's see the third method, that is froth flotation process. Froth basically is the formation of a foam, that is basically we see the jhag that is being formed. It is an important method, students. How it is an important method? Let us understand this. Here basically are the impurities that are present inside. Here basically is what is present, ma'am. Impurity is present. Understand this. Here is impurity that is kept inside. Now what basically happens? Here inside is powdered ore and there is water and there is a pine oil. What basically we are keeping? We are keeping powdered form of ore. Powdered form of ore. Then water is also present and pine oil is also present. What is present? Pine oil is also present. Here we also take, some different, see here, froth flotation agent is also used, right? Now here we are passing air from the top. Why we are passing air from the top? When we pass air from the top, this basically thing will start to rotate. It will rotate. When it will rotate, it will create, foam. What it will do? It will create foam. It will create foam. That foam will move in the upward direction, which is referred to as froth. Froth is basically a form of foam that is created on passing the air, right? Yes. So what happens? The gang particles will get separated at the down, the impurities will be left down, and our ore particle will come in the form of small particles in the form of foam. It will come in the upper layer, right? This is froth flotation process. Let's understand this. Finely powdered ore is mixed with water, pine oil, that is frother, and ethyl xanthate or potassium ethyl xanthate, that is collector in a big tank. Okay. You have to learn what you have kept. This is important one. The whole mixture is extracted with air. You pass the air, ore particles wetted with oil. Now you should know, see, we are adding ore particles with oil, no? So it will be wetted with oil, and oil basically will not mix into the water, it will come above. So above one, the foam one is basically the ore, right? So the ore particles wetted with oil come in the froth, that means in the form of foam, and taken off. While impurities wetted with water will settle at the base, right? Here foaming agent is pinol and froth stabilizers. Here you are using the froth stabilizers such as cresol and aniline. So such questions can also be asked basically, that what exactly you are using over here, right? Collector used is ethyl xanthate and potassium ethyl xanthate. So this from this questions are generally asked. Clear everyone? This was froth flotation process. Now comes the process of leaching. Yeah, now this process basically on over there I told you know when I was telling about chemical separation method, that there are many methods, because it by chance by here it is written this, so this is wrong, you very well know. Chemical separation methods we are going to understand in depth now. Let's understand about chemical separation. You can mention it, the leaching is chemical separation method. In chemical separation method, what exactly is going to happen? Let's understand this. Leaching is often used if the ore is soluble in some suitable solvent. We are going to take a suitable solvent and it should get dissolved into it. This is what is important part. Okay, example acid, base and suitable chemical reagents. Now, this is important. Leaching of alumina from bauxite. Leaching of alumina from bauxite. Bauxite is basically ore of aluminium, right? So let's see how we are going to do the leaching process, the chemical method. Principal ore of aluminium bauxite usually contains SiO2. We have understood SiO2 is impurity. No, we have studied when I was telling about slag and flux, right? Iron oxides and titanium oxide as impurity. So it basically contains these three impurities: SiO2, TiO2, and iron oxide, FeO. Now concentration is carried out. Now what is concentration? The cleaning process. It is carried out by digesting the powdered ore with a concentrated solution of NaOH, and you are providing it at a particular temperature. So basically you have taken the oxide, the bauxite ore. Bauxite is Al2O3 dot 2H2O, right? And now you are mixing it with concentrated solution of NaOH so that the concentration process can be done out. Cleaning can be done. This way Al2O3 is leached out as sodium aluminate, and also SiO2 as sodium silicate. They come out as a product, leaving behind the impurities, iron oxide and the titanium oxide. So this is the reaction, students. Here you are using Al2O3 with NaOH and water. You will be obtaining this product over here. The aluminate in the solution is neutralized by passing CO2 gas, and hydrated, this is precipitated. At this stage, solution is sealed with freshly prepared samples of hydrated this, which indicates the precipitation process. You just need to understand this process, that what over here is happening. These two lines are really very important. You do concentration with NaOH. Concentration means cleaning. When you do this process at 473 Kelvin to 523 Kelvin, you are going to get what? Really sorry. You are going to get what? You will see that Al2O3 will be taken out as sodium aluminate and SiO2 as sodium silicate. Rest oxides will come out, right? So this is again the the process of doing the concentration. That means the cleaning process, if I'll talk about, that is through chemical methods. Now over here we are going to do which by other examples. Now here we are going to do the concentration of gold, all of these. In the previous case I told you of aluminium, here of silver and gold. So in the metallurgy of silver and that of gold, the respective metal ore is leached out with a solution of NaCN and KCN with their cyanides. Okay, we are going to do this with their cyanides. For example, this is your metal, that is Ag and Au. This is your impure metal. You are taking the cyanide, Cn negative. You are reacting with water and with O2. Remember, with O2 you have to do, otherwise in the absence of O2 it won't take place. So you are going to obtain this complex. Now this complex on further reaction with zinc. Zinc basically will act over here as a reducing agent. Zinc basically will react as a reducing agent, and you are going to obtain the pure metal. So basically you took the impure one, reacted with Cn negative and O2 and water, you got in complex, which on further reactant with zinc, which act as a reducing agent, you are going to obtain the pure metal over here. So this is the initial method of, the metallurgical process, that is our concentration. Now let's do the next way. Let's move on to the next one, that is crushing of ores. That let's understand about crushing. See, big lumps of one obtained from Earth's crust are crushed into smaller pieces with the help of jaw crushers or grinders. This process is crushing. Crushing is means converting them into the powdered form. Right now, after this, after crushing, we are going to do the conversion of ores. Conversion of ore into oxides. See, till now we have understood about concentration. Now comes the second, that is conversion of ores into its oxide. Now basically this is done by two methods, that is by calcination and by roasting. Calcination and roasting. Let's understand about them in detail. Yeah, so see, the concentrated ore must be converted into a form which is suitable for reduction. Yes. Now see, usually the sulfide ore is converted to oxide before reduction. Oxides are easier to reduce. Thus, see, that's why we are converting now ore into oxides, because they're easily to reduce. Next, thus isolation of metals from concentrated involve two major steps. Conversion into oxide. First, you are doing the concentration. Then you will convert your ore into oxide. Then reduction of that oxide to metal will take place. Clear, everyone? Okay. See. Now see, this is basically what is happening. Extraction of crude metal. How you will extract? Conversion of ore into oxides, either by roasting or by calcination. When you will do this process, the conversion of ore into oxide, then you have to do the reduction of that metal oxide, and that reduction can occur by three methods, methods, that is smelting, reduction by carbon, hydrogen, or by metal, or by auto reduction. Okay, that is self reduction also method. So let's see conversion into oxide. So where we can convert with the help of calcination and roasting. In calcination, basically we take absence of air, and in roasting we take, presence of air. In calcination, there is limited, if air is present, it is present in limited amount. What exactly happens? It is a process of heating. Here you are going to heat it. For example, if I'm saying you have to heat, the ore, you have to heat the ore and you have to convert it into oxide. Let us say if we have CaCO3, you're going to heat it out, students. You are going to obtain CaO, and CO2 will be liberated out. Right? So this is calcination process, no requirement of air, in the absence of air. So this is the process of heating concentrated ore strongly in the limited supply of air or in the absence of air. Process of calcination brings about the following changes. Now, see, basically there are examples they have given you. For example, FeCO3, if you heat, it will convert into Fu and CO2, which is siderite when you are heating it. Then is PbC. This is no need. If you want to learn, you can learn, but no requirement. Yes. Next is CaCO3. Which I have already told you it's important, and calamine is also important. ZnCO3 will convert into ZnO plus CO2. Then students, let's talk about the roasting process. See, in roasting, basically it occurs in the presence of air. In the presence of air, only that can take place. Let us take an example that if I have a ZnS and I am reacting it with O2, basically. So what I'm going to form? I'm going to form ZnO. I'm converting into oxide. ZnO is a zinc oxide plus SO2 will be liberated. So it is also conversion into oxide, but in the presence of air. So it is a process of heating the concentrated ore strongly in excess of air or O2 below its melting point. Roasting is an exothermic process. Once started, it does not require addition heating. When someone started, it will complete automatically. So there are some examples. See, here they have formed PbO, here they have formed ZnO, here they have formed Cu2O. So all of these are oxides basically, and all of these occurs in the presence of air, student. All of these are occurring in the presence of air. So it is very easy for you to understand that here you can see it is O2, it is reacting with O2 with O2. Yes, simple. Let's move on to the next part. And one more thing, roasting generally occurs in sulfide ores, PbS, ZnS, Cu2S, this part. Yes, students, now comes a reduction of metal oxides into the free metals. How can you do the reduction? Now, you have converted your ore into oxide. You will now do the reduction process, right? So that can be done by four methods. The very first is carbon reduction, second is reduction by other metal, third is self-reduction, fourth is electrolytic reduction, right? So if I move on with the first part, that is basically the carbon reduction, that is basically the smelting process. Carbon reduction basically, students, is your smelting process. Which process, ma'am? Smelting process. This is smelting process. Here I have to tell you that here you are going to take different reducing agents. So the best reducing agent is carbon. Here you are going to take the best reducing agent, that is carbon. Even, CO is used as a reducing agent. Carbon monoxide is also reduced as a reducing agent. So let me give an example. For example, if you have obtained a PbO, This is your lead oxide now. You will react it with carbon. It will act as a reducing agent. You will get your Pb. You will get your what? Pb, ma'am. And your carbon monoxide will be released. So this is the way how you are going to obtain your metals. Clear, everybody? Similarly, you can go for ZNO. ZNO plus carbon will give you Zn plus Co. This is zinc oxide reacting with carbon because carbon is a good reducing agent. You will obtain zinc and CO will be liberated. So this is carbon reduction method, and you can even take CO as a good reducing agent. Clear, everyone? And if I'll talk about now the reduction by other metals, so we can take in case of aluminium. Aluminium is a very good reducing agent. Again, we can even do the reduction process with the help of this. For example, if I'll take now an oxide of Cr2O3, we are going to react it with aluminium. What will happen? We will obtain chromium. Right? And this chromium will be obtained in the molten form, students. In which form, ma'am? In molten form, liberating what? Al2O3. So this is basically reduction by other metals. Now, these all four methods, students, let me tell you, are very, very important. Very, very important. Okay. Now let's talk about the self-reduction method. See, self-reduction method is also referred to as the auto-reduction method. Okay. Now, basically, it is used for very less reactive metals. If you want to write down, used for very less reactive metals. Very less reactive metals, if I'll talk about. For example, if you have Cu2s, you will react with O2. Okay, here partial roasting will take place. Now, in this process, what are you going to obtain? You will get SO2 as a byproduct, and you will obtain Cu2O. Okay, so this is the process that is self-reduction. It is going to do the reduction process by itself. Now, what will happen? The Cu2 that you obtained will further react with Cu2s. What are you going to obtain now? You're going to obtain now again the copper. Copper will be liberated out, SO2 will be released. So by this way, you're going to obtain the copper. Clear, everybody? Now comes what is electrolytic, ma'am? Electrolytic method. Basically, it is used for highly reactive one. This is for less reactive one. That is used for highly reactive ones. See, in electrolytic, basically, we are going to use the anode and the cathode, and then we are going to connect them. If I'll take the case of NaCl, Na will be coming at, cathode, Cl will come at anode. So this is the process of electrolytic reduction. Now, students, comes the next part, that is basically the thermodynamic aspect and the Lingam diagram. Let's talk about it in detail. See, basically, we are going to start with the Lingam diagram. What is a Lingam diagram? What does it depict? It depicts that whether a reaction is spontaneous or not, whether a reaction is going to take place or not. So for a spontaneous reaction, delta G will always be negative. This is the thermodynamic aspect that we are going to study, right? So Gibbs free energy change, if we are going to know, that delta G is equivalent to delta H minus T delta S, right? And delta G will always remain negative for a spontaneous reaction. And Lingam diagram is used for that purpose only. So here comes the Lingam diagram, which depicts that whether a reaction is spontaneous or not. So it tells about spontaneity. It is a graph between delta G naught and between the temperature. Okay, between the temperature. Moreover, if you're going to see that these are the curves and they are changing, slopes are being changing, like it is coming like this, it is changing. What does the slope change depicts? The slope change depicts that there is a phase change. That means from solid to liquid, or from liquid to gaseous, or from gaseous to solid. The phase change occurs over here, right? One more thing, always remember how to study Lingam diagram. For example, this is the curve for magnesium, this is the curve for aluminium, right? So here magnesium is at a lower position than aluminium. So what is the rule of this? That below metal is going to reduce above metals oxide. So magnesium can reduce aluminium oxide Al2O3 and will convert into aluminium and will get magnesium oxide. At what temperature? This is the temperature in which we can see curve is below aluminium, and here it is above aluminium. So this temperature is near about 600 Kelvin. So below 600 Kelvin, magnesium curve is below, so it can reduce the above one. And after 1600 Kelvin, after 1600 Kelvin, aluminium curve is below, magnesium is above. So aluminium can reduce the oxide of magnesium and will convert into Al2O3, and magnesium will be released. So in all of these reactions, you have to see this only. The lower metal is going to reduce the oxide of the higher metal. Very simple thing, students. Do remember this. It is very, very easy, right? Let's move on to the next part now. Let's understand this only in detail. It is written. What are the limitations? What are the limitations? The limitation is it was not able to explain the kinetics of a reaction, the rate by which a reaction takes place, or it is first order, second order, which kind of. It is not able to explain. Moreover, whenever you see there is a phase change from solid to liquid or a slope change, there occurs equilibrium. So they are saying in the solid particles, equilibrium does not attain. So this is again the wrong one. Okay, this is again, it cannot explain that part. This I have already explained you that yes, magnesium is going to reduce aluminum oxide, forming that process. Clear, students? This was about Ellingham diagram. Now comes your next process. Now, this is basically the blast furnace reaction, which many of the students even don't know. See, in the blast furnace process, what actually happens, let us understand this in detail. Now we have done the concentration of ore. Now comes the extraction processes. How it is going to take place? Basically, see, students, this is, you can see this question from blast furnace is asked that up to what extent the temperature is provided in the blast furnace. So when you see from top to bottom, temperature is increasing. So the highest temperature can be 2170 Kelvin. And here is your pig iron that is obtained. Yes, here is your pig iron that is obtained. This is your slag. And yes, you need to learn some of the reactions. The reactions that you need to learn over here, I will be putting a tick, that is CaCO3 converts into CaO plus CO2. This you have to learn. This slag 1 reaction, you already know that CaO is going to react with SiO2 impurity, will produce a slag, right? Similarly, they have told you about the reaction of a coke. So both of these are important. And yes, here you are going to obtain pig iron. So difference between the types of iron, you should know what is wrought iron, what is pig iron. I will let you know about that as well. Let's understand about that as well. So these are the reactions that are involved but in the blast furnace process. They have written all the reactions. Yes, I have tick over there. You can learn that reactions. Now this comes the important part, that is types of iron that you should know. See, basically there are three type of iron. One is cast iron, wrought iron if I'll talk about, and then they're talking about the steel, right? So in cast iron, the chemical composition is iron is about 93%. It is very hard, cannot be permanently magnetized. If I'll talk about the wrought one, and it is iron is 99.5% to 99.8%. Carbon and impurity, they have already told you. It is soft in nature, and it is magnetization is not permanent, but it is easy. Then comes your steel, which is medium hard. It has a medium hardness and it can be permanently magnetized. Yeah, so you should know the difference between that as well. Now, students, come the extraction of certain metals. How you are going to extract those certain metals? So we are going to start with the process of aluminium. How extraction of aluminium can occur? So we are going to do the purification of bauxite. Bauxite is ore of aluminium, no? So first method is the by Bayer's method. Which method, ma'am? Bayer's method. So basically this is used for red bauxite, and for white bauxite you are going to use the Serpuk's method. Okay, so for red bauxite you are going to use Bayer's method, and for white one Serpuk's method. Now see, Bayer's method is used for red bauxite, which contains Fe2O3 and silicates as an impurity, right? So now this is basically the bauxite or the red bauxite. You will react with NaOH. In the previous case also I told you you have to react with NaOH. You will get, this is this part which is a basically soluble portion and water. Fe2O3 is insoluble. It will separate out as red mud by filtration. Okay, so you will separate the impurity very easily. Okay, the next part is it induces the precipitation of AlO3 OH thrice, and it is filtered, leaving behind silicates in the solution. So yes, at last what you are going to get? You are going to obtain AlOH thrice, which on further reaction at a higher temperature will give you Al2O3. So this is extraction of aluminium from this process. Right now, next is also, even for red bauxite, you can obtain Hall's method if you contain Fe2O3 and silicates as an impurity. So this is the Hall's method which can be used for the purification, and then comes for the Serpuk's method for the white bauxite one, right, where silica is used as an impurity. So this is white bauxite. You will react with carbon and N2, important one. In electric furnace method, you will obtain Al and CON water. That ALN will further react with water, AlOH thrice. In the previous case also that was produced, here also, right? This will be produced, which on further heating will give you Al2O3 and water respect. Clear, everyone? Now next method comes out to be the electrolytic reduction method. Which method, ma'am? The electrolytic reduction one. Let's see. In electrolytic reduction, Hall-Heroth's process, the name itself says they will ask you directly the name of it. So you should know the name of it as well, right? The purified Al2O3 is mixed with Na3AlF, that is cryolite and phosphor. Okay, I already told you that is the neutral flux cryolite and phosphor, right? So you can even learn their formulas if you want to, which lowers the melting point of the mixture and brings conductivity. Now, fused matrix electrolyte steel cathode is taken as a steel cathode is taken and graphite anode are used over there. So basically, you're doing again the electrochemical processes you have understood in electrochemistry. So same process is going to occur in the presence of electricity that is going to happen. You're going to take two electrodes, cathode and anode, and the reduction process will start. Graphite anode is useful here for the reduction of metal, right? Here you can obtain aluminium as a metal very easily. Clear? Now students, they are saying these are the reactions for the cathodic and the anodic one. You should learn both of the reactions for the cathodic as well as for the anodic one. Then comes your zone refining method, students. See, refining basically is done, there are two types of in the physical refining. One is liquefaction, distillation, and then the zone refining. Liquefaction, distillation, and the zone refining one. If I'll talk about liquefaction, let's write over here only. If I'll talk about the liquefaction, these are the physical methods of refining, okay? If I'll talk about the liquefaction method, students, in liquefaction method, what happens is melting point of impurity is more. Remember that. Melting point of impurity is more. So it is based upon the melting points first of all, and that of metal is less. And that of metal is less. Metal melting point is low and impurity melting point is high. So what basically is going to happen, this is used for PB, SB, SN and all of that, right? The metal will basically flow down the surface and impurity will be left over. So by this way, you can do the refining process. Similarly, we have a distillation process. We have one more process, that is distillation. That is which process, ma'am? Distillation. In distillation process, the boiling point is basically of metal is taking as low and impurity has high one. The boiling point and the melting point. But over here, vapors are created. It is used for ZnCd mercury, zinc, cadmium, mercury. Here vapors are created. Vapors, through the help of vapors, we can do the separation method. Now comes which method, ma'am? The zone refining method. See, basically zone refining is also an easy one. Let's understand this. Here you're going to take a roller and everything happens. Let's see. It is highly purified metal is obtained by this method. For example, see, this is used for the production of, semiconductors. For semiconductors. Silicon, germanium, gallium, for all of them. The principle underlying the process is metal and impurities have differences in their solubilities. In the previous case, they have difference in melting point and boiling point. A circular mobile heater fitted around a rod of impure metal is slowly moved. It moves like this. I will show you how. It moves around it like this, right? So this is a circular heater that is kept over here. This is recrystallized pure germanium. Here is impure one. So it gets heat at a particular point and then the cooling process occur. So basically, see over here it is written, at the heated zone the red melts as the heater moves, the impurity pass into the molten zone, while pure metal is going to crystallize when cooling is done, right? So this is basically the zone refining. Now comes the last one, that is the vapor phase refining method. Which method, ma'am? The vapor phase refining method. See, in vapor phase refining method, basically there are different methods. The very first that you're going to do is extraction of nickels by Mond's process. The names are asked generally, students. Next is von Eckerl D. Beer method. Okay, so these are the various methods that are generally used. This is used for titanium, zirconium, hafnium, bismuth. This is used for them. So let's read about it. In vapor phase refining method, what happened? In this method, metal is converted into volatile compound and then collected out. It is then heated and so that it gets decomposed to give the pure metals. Now there are two requirements for this. The first, metal should form a volatile compound, then only it is possible. Next, volatile compound should be easily decomposable. So first method is extraction of nickel from the Mons process. Okay, nickel forms a complete complex, okay, with carbon monoxide, that is NiCO4. Okay, so basically what happens is, in this particularly, first of all, we are going to react it with carbon. We will obtain carbon monoxide, which reacts with nickel to form this complex. This complex on further heating at 200 degrees Celsius will give you pure nickel. Now this is pure nickel. Here you took impure one. Now you got pure nickel. Now the last one is von Eckerl D. Boyer's method. There are a small amount of pure metals like tin, zirconium, bismuth, and all of these are used over here, right? For these, it is used for the purification of them. This process is based on the fact that iodides are the least stable of the halides. How it takes place, like pure titanium, if you are taking it, will react with I2. It will form a complex. Now that complex on further heating, like in the previous case, we give 200 degrees Celsius, here we are giving 1400 degrees Celsius. You are going to obtain the pure Ti. This is impure, that is the pure you are obtaining. In the same way, students, in the same way. Clear, everyone? Now, students, this ends our complete lecture over here. This ends our complete metallurgy chapter over here. We have completed this metallurgy chapter in this one short lecture. I hope so. This is now clear to you. Now, students, practice as many as questions as you can. Now, this metallurgy chapter from NCERT is given with the name General Principles and Isolations and Purification of Metals. So you can just read from NCERT also, though we have completed all of the part over here. I hope so it was helpful for you. Now, we shall be meeting in the next class. Till then, keep smiling, keep learning. Thank you so much and take care, everyone. Bye-bye.